Hello, everyone. The topic of our presentation is AVE-CLIP, audio clip-based multi-window temporal transformer for audio-visual event localization. I'm Tanvir Mahmud, and I'm working under Professor Marculescu. We are from the Department of Electrical and Computer Engineering at the University of Texas at Austin. So what is an audio-visual event? An audio-visual event is defined by the audio-visual correspondence over certain temporal duration. So here we can see a person is speaking and his voice is audible in all of the frames. But when the person's voice is audible and the person is visible, an audiovisual event is identified. So here we can see only 3 frames represent the audiovisual event of man speaking. Here is the overview of the methodology. So we can see we are using 3 stages of training. In the stage 1, we introduce a contrastive fine-tuning of audio clip encoders. The audio clip encoders are pre-trained on large scale of image-audio pairs. But we fine-tune these audio clip encoders with the image and audio pairs extracted from our AVE dataset. So it generates grounded multimodal features for AVEs through the contrastive fine-tuning. And in stage 2, we extract the video features with fine-tuned audio clip encoders. This aggregated temporal and audio features helps us doing multimodal fusion in the next process. So on the stage 3, we operate on the extracted features with multi-scale training on varying temporal windows with post-processing. Here we introduce a bunch of techniques. We introduce the multi-window temporal fusion to operate on different temporal windows. We introduce event-guided temporal attention to focus more attention into the event region, and we refine the event features with the refiner. And finally, we do the post-processing to utilize the sequential nature of the events and backgrounds. So here is the multi-window temporal fusion, which is a basic building block. So in here, we do 3 stages of operation. Initially, we split the aggregated temporal multimodal features into different temporal windows. Then we do some multi-domain fusion on each of these temporal windows. And then we aggregate all the features from different temporal windows. And we introduced a multi-domain fusion that was utilized in the multi-window temporal fusion process. So we do 2 stages of attention. One is the temporal attention, another one is the feature attention. This 2 attention approach helps to recalibrate both the temporal and feature domains. And here are the overview of our results. So we compare our performance with multimodal approach and unimodal approach. So we can see that our approach outperforms the AVE transformer by a large margin and achieves 83.7% of state-of-the-art accuracy. We also outperforms other approach by a large margin. And in table 2, we compare the performance of the audio clip encoders. So we can see by incorporation of the audio clip encoder without fine-tuning, we achieve 81.1%. But by further fine-tuning, we achieve the state-of-the-art accuracy of 83.7%. Here are some of the qualitative results. So we show performance on 2 events, that is helicopter and violin events, and we compare the performance with the baseline approach PSP. So we can see our approach reduces the false positives in many critical regions. In summary, we introduced a multimodal contrastive fine-tuning. For extending audio clip, we introduced a multi-scale temporal training with multi-domain attention. Our method achieves state-of-the-art performance, and it can be extended on multiple applications. This research was supported in part by the Office of Novel Research Minerva Program and UT Cockley School of Engineering Doctoral Fellowship. Thank you, everyone.